Good afternoon. We now understand op-amps at the control source level, at the level of GMs in some detail. We can now combine that with our knowledge of the transistor level building blocks to realize the op-amps. Okay, so the single stage op-amps are just a transconductance transconductor with differential input. Okay, so this is the single stage op-amp. Now the way to implement this is using a differential pair with a current mirror load. Okay, now what is that? I'll assume that we have an NMOS differential pair and a PMOS current mirror load. This is the input and you have the output over there. Okay, I think you know this already, so I won't spend too much time on this. This incrementally is equivalent to a transconductor, a GM, in parallel with some output conductance. Okay, so if the inputs are biased at some common mode voltage, the common mode voltage is nothing but the average of the input voltages, right? And let's say this current is 2I0, then the current in each of these branches will be I0. Okay, and from there we can form the equivalent and so on. And let's say this is the large signal output VO. So first is the DC incremental small signal picture. Okay, what is that? That is just if the difference voltage is VD, let's say you have VD by 2 and minus VD by 2. We have a conductance GDS1 plus GDS3. So again, because M1 and M2 are matched, I will use 1 for subscript 1 for both of them, and M3 and M4 are matched, I'll use the subscript 3 for both of them. So this is VO. Okay, so this you know. And large signal wise, you have to specify the swing limits. Okay, so essentially this op-amp has 2 inputs and 1 output. Okay, so you have 2 different swing limits. Now that is what I mean is that this is the common reference node and you have 2 inputs VIP and VIM and 1 output. So anytime you have that, of course you have 2 different transfer functions, 2 different inputs, right? VIP and VIM. But functionally it doesn't make sense to treat VIP and VIM separately. We still have to have 2 inputs. What makes sense is to specify everything in terms of the differential difference voltage. Okay, whenever you have a linear circuit like this, what will be the output? The output will be of the form A1 VIP plus A2 VIM. Okay. Now, functionally, what is it that we want? We want to have A2 to be minus A1. That is, we should react only to the difference between the inputs. We should not react to the average value. Okay, that's what common mode rejection is, right? So, if VD is basically VIP plus VIM by 2, sorry, VIP minus VIM, and the VID is that, and VICM is VIP plus VIM by 2. Okay. So you can either choose VIP and VIM as the variables or VID and VICM. We will choose VID and VICM because functionally that's what is relevant. Okay. So the gain from VID to the output should be large, and the gain from VICM to the output should be 0. Okay. Now when it turns out it's not exactly 0, we'll see. This is the picture from the, let me call this VID to indicate the input difference. Okay. Why do you need common mode rejection? What happens if you don't have common mode rejection? You have calculated common mode gain and common mode rejection earlier, right? But why do we care? What parasite? No, I think you are mixing up things. I am talking about the small signal common mode gain, right? Which noise? Okay, fine. Now, if the noise is in opposite direction, it will get amplified, right? So, true, but what is it that we are looking for here? I mean, some example. So, there are many contexts in which, first of all, you will have an error. Okay, so you can do this calculation. I won't do it here, but again, you take the same, exact same opamp circuit which we have analyzed some bazillion times. Okay. So now we have been for DC. This is the model we use, right? But let us say that we say that VO is AD times VID, which is the conventional differential gain, plus ACM times VICM. What is VICM? So this is VIP, VIM. VID is VIP minus VIM, and VICM is VIP plus VIM by 2. So this is just regular linear circuit analysis. You assume that this is the model for the op-amp and you calculate what the output is. Okay. Now, just to give you a context for where common mode rejection may be important, there are many cases. Like I said, the common noise will be amplified, but we are talking about the open loop circuit, right? So, for instance, now here I am talking about the full amplifier. One of the common cases is you have, let's say, a battery, and you have some circuit powered from it. Okay. And one of the common things that you see is to keep track of the state of the battery. Obviously, like all of you have phones and it shows you how much battery is remaining. And that is done by what is known as Coulomb counting. That is, you measure how much current is flowing, basically how much charge is coming out of the battery. How do you measure how much current is flowing in a circuit? What do you do? Yeah, but I mean, is that what your mobile phone is doing inside? From where? So one thing is to measure the current, you have to place something here, okay, in series, wherever the current is flowing. Now, the moment you place it, it will have some drop, whatever you have, okay. If that drop is significant, it is completely wasted power, right? Because just for measurement, you are wasting that power, okay. So, in fact, that is how it is measured. You have a small resistor. The resistance should be small so that you don't waste much. And how do you measure the current? You can measure the voltage across that. So now, let's say the battery is some 3.7 volts or something, and you don't want to waste too much power. So maybe the maximum voltage drop across this could be in the millivolts. Let's say 5 millivolts. Okay. So if you look at this pair of signals, okay, what is the common mode voltage here? What is the common mode voltage? If you look at those two, approximately what is it? 3.7 volts, right? Basically, it is 3.7 and this is 3.695. Okay, so the average is almost 3.7 and the difference is 0.005. So now you can see if whatever circuit you have to measure this also reacts to the common mode, you can have a substantial error, right? Because the common mode is almost 1000 times more than the differential signal that you're trying to measure, right? If this was 3.7 millivolts, the common mode would be 1000 times more than that. So even if your common mode gain is small, the large common mode value can have an effect. Okay. So this is the type of, this is one particular example. There are many cases in which this common mode becomes important. Now, of course, the next thing is you can ask why not put the resistor here where the common mode is small, but typically it is not easy to, that is the common ground for where lots of things come together. It's usually a lot more difficult to lift that up than do it from the supply line. Okay. In fact, this part could be part of the battery itself. The battery itself has some small resistor built in and it has some outputs also to give you the state of the charge. This is just to tell you there are many cases where you will have a you have to measure a small difference around a large average value. Okay, so that is inherently difficult. By the way, that's difficult even in calculations, right? Whenever you are trying to subtract two large numbers to get us where the difference is small, it's very easy to make errors, right? If you round off badly, then if you are measuring, like if you are subtracting, I don't know, 10,000 minus 9,999, and then you make some small errors in the 10,000 and 9,999, you can get a very large error in the difference. Okay. So similarly, here in general, measuring small differences around large voltages is difficult. Large average values is difficult. So that's why common mode rejection is important. And there is something called common mode rejection ratio. You are familiar with this? What is it? It's AD by ACM. Okay. Why is this particular quantity important? You can analyze the circuit and you will see. Okay. So for now, what we'll do is we just will evaluate ACM of this. Okay. What is the common mode gain of this? How would you go about evaluating? How would you evaluate the common mode picture? So what does the common mode picture mean? I mean, I will show the common mode increment as VICM. It is operating around some VCM, and from there I change both the values by the same amount slightly. I want to see how the output changes. Okay, how would I analyze this? What's the easiest way to analyze this one? Half. Really? When can you use the half circuit? No, not just same input. Circuit has to be the same on two sides. Is it symmetrical? Huh? Making a? So is it symmetrical or not? Is the circuit symmetrical? Clearly not. I mean, if you look at the drawing, it is not. But let us say there is no mismatch. Okay. What can you say about the relationship between this voltage and that voltage? When you have only a common mode input, That is, when these two voltages are the same, okay, there is no VID, VID is 0. What can you say about this voltage and that voltage? They have to be the same, okay? Because if they are not the same, this argument you must have heard before, that if you imagine some output conductance value, if these two voltages are not the same, what happens is, what happens? So if let's say you assume VO is more than this voltage, then by looking at M1 and M2, you will conclude that M2 has more current, because both of them have the same VGS, but M2 has higher VDS. But looking at M3 and M4, M3 has higher VDS, and you will conclude that that will drawing more current. So clearly this is contradictory. So the only solution is for these two voltages to be exactly the same in absence of mismatch. So what next? We started by asking how will I analyze this for common mode. So what should I do now? Basically, yeah, we can essentially short these two and analyze them, okay, for common mode. Because if you have common mode, these two will be the same no matter what. So I'll just short them and see what the output will be. Is this part okay? Now this single stage op amp you need to understand well, because any other op amp, the first stage is invariably the single stage op amp. Okay. Now you're all sufficiently familiar with the circuit that circuits that every time I'm not going to draw the incremental equivalent. I think from the transistor picture you will be able to imagine that. Okay. So these two are shorted, and the operating point here is VCM, and you have some 2I0 flowing there. Okay. Over that, I have some incremental voltage. Similarly, the operating point at the output would be VDD minus VSG3 at a current of I0, right? I have taken 2I0 to be the tail current source, so I have I0 and I0 on either side. So now the question is, what is the increment at the output? How would you do this? What is the increment at the output? What kind of circuit is this? With the drains shorted, what kind of circuit is this? So if you look at these two, M1 and M2, all three terminals are essentially shorted, right? The drains are shorted, the gates are the same voltage, sources are shorted. So the two transistors are in parallel, and I'll just write it as 2 times M1. It means that the width is doubled. What about M3 and M4? Again, all the terminals are shorted. So you have a diode connected transistor, which is 2 times M3. Okay. And here, incrementally, this is grounded, and incrementally I have VICM there, and here I have to find out what the increment is. Okay. So what kind of an amplifier is it from here to there? Common source, yeah. Common source. Where is the source now? What is the source voltage of that? You have seen the circuit, right? What is it? So this part of it Do you recognize this or not? What is it? Huh? The input is here. The cascode, the input is there. Okay, and this is grounded. So it's a source degenerated amplifier. You are familiar with this, right? What is this? What is this alone? This is a particular type of current source. What is it? This is a voltage controlled current source. Okay. If the GM is very large, there is feedback, right? If the GM is very large, what happens to the incremental VGS? It will be 0. Okay. This is in feedback. There is negative feedback in this. This I think you have seen in the previous course. So if the GM is very large, incremental VGS is 0. So the input appears here, and if I call this RS, the incremental current will be VI by RS. With finite GM, there will be some voltage and you can make some correction for it, and that turns out to be VI by RS times GM RS by 1 plus GM RS. Okay? Is it okay or not? Some of you are acting like you are seeing this for the first time. So because this basic stuff we have to take for granted if we have to make somewhat quick progress, but if you have forgotten this, go and analyze it. With your circuit analysis skills, you'll be able to easily do this. Okay. So now, how is this equivalent to this? What is this resistance? It is the output resistance of this. Okay, because the gate is grounded, the incremental current source inside is open. Only its output resistance remains. Okay. So now, what is the incremental current flowing here? Approximately. Or okay, first let me start with this. What is the incremental voltage at the source, at the drain of M0? What is it? Again, looking at the other circuit, what is it? What kind of circuit is it between this and that? That does the input, this is the output. What kind of circuit is it? It's a source follower, right? It's a voltage controlled voltage source. Common, yeah. So what is this incremental voltage? It is VI CM. Okay. Now in reality, it will have some other factor, which is GM. What is GM? What is the GM that appears here? 2 times GM1, because 2 of these are in parallel. Okay. 2 GM1 by 1 plus 2 GM1, sorry, 2 GM1 RDS 0, RDS 0. Okay. But it's okay to approximate this by VICM, right? We'll just do that. And what is the incremental current flowing there? So this divided by RDS 0, okay, which I'll say it is VICM by RDS 0, okay. And what is the load impedance of this? So if I had RL, this voltage would be minus VI RL by RS approximately. So what is the RL that is appearing now? 1 by 2 GM3. Okay, GM3 there are 2 of them in parallel. It's and they're diode connected. So effectively it's a resistance of 1 by 2 GM3. So the output voltage will be VICM 1 by 2 GM3 RDS 0. Okay, is that fine? So that is the common mode gain. Okay. So ACM, this is DC common mode gain is 1 by 2 GM3 RDS 0. Okay. So you can see actually the load impedance for the differential case is higher, right? It is GDS1, I mean the load conductance is lower, GDS1 plus GDS3, whereas the load conductance for the common mode case is much higher, okay? So we'll see this more and more. Later we'll come to common mode feedback circuits for fully differential cases. So one of the ways of reducing the common mode gain is to make the load behave like a low impedance for common mode signals and high impedance for differential signals, okay? So what is the common mode rejection now? So by the way, I mean the actual gain is negative, but only the magnitude is shown when you show the ACM. So what is the common mode rejection ratio? You will see that it is the ratio of these two, right? It's GM1 times RDS1 parallel RDS3. This is the differential gain times 2 GM3 RDS0. Okay. So this is actually a substantial common mode rejection. Okay. So in fact, if the gain is of the order of a few tenths, the common mode gain is the reciprocal of that, of the order of like 1 by 10 or something like that. So the common mode rejection is very high. That's why also this stage is very popular. In fact, this is one of the few stages that only reacts to the differential mode. Okay. In fact, what do you have to do to improve the common mode rejection? Which is the, let's say you don't want to change anything else and you want to change only the common mode rejection. What is it that you have to improve in the circuit? What is it? RDS 0. Okay, the current source has to become better. If the tail current source is ideal, then the common mode gain will be 0. Okay, the common mode gain is coming only because as this voltage changes, both of them change together, the source voltage also changes. When the source voltage changes, if the current doesn't change, then nothing happens. The top of the circuit doesn't see it at all, the top part. Okay. So now, if the current changes, then it will see that there will be some change in the current there and you will have some change in the voltage. Okay. This is also why at high frequencies, you will have a parasitic capacitance from here to ground. So if you have a high frequency common mode signal, then instead of GDS 0, you will have whatever impedance you have at high frequencies. So at high frequencies, the common mode rejection does get worse. Okay. We don't have to worry about that now, but at least you should know how to calculate the common mode gain and what is it that one single element that controls the common mode gain is the output resistance of the tail current source. The better the tail current source, the better the common mode rejection. Okay. And of course, to improve high frequency common mode rejection, you should also minimize the parasitic capacitance from that node. Is this okay? So sometimes just to improve common mode rejection, you may have to use a cascade current source instead of a regular current source. So that instead of RDS 0, you have a much higher resistance. Okay. Of course, anytime you use a cascade, you have to fit more transistors and you will lose headroom. Any questions about this? So this level of circuit analysis you can do yourselves because all this is simply related to the basic building blocks. So I'm just going to go somewhat quickly through them. But if you don't understand something, please ask so that you don't miss out something big. This is okay? No, we don't have higher resistance at high frequencies. We have a higher admittance. That is, you will have this by itself will have RDS 0, but from this node there will be some parasitic capacitor C0. So if you look at the admittance here, that will be 1 by RDS 0 plus SC0, right? So the admittance increases. So for a given change in voltage, at low frequencies you have current flowing only through RDS 0. At high frequencies you also have this. So what happens is more current change will be there. So the common mode gain actually increases with increasing frequency. In the worst case, you imagine a very large capacitance here which shorts it to ground. Then the common mode gain and the differential gain will be almost the same. Is this okay? So what all parameters were there in the data sheet? What else do we have to calculate? I mean, you have seen opamp data sheets, right? What all does it have? So that, yeah, unity gain frequency or the gain bandwidth product. Okay. Maybe there is also a phase margin for unity feedback and so on. So first we'll, these are the two DC small signal parameters, and then you have sort of AC characteristics, the unity gain frequency or gain bandwidth product. Okay. So you have the capacitance anyway, right? And the incremental equivalent is so what is omega u in this case? We've already calculated this. What is omega u? We've done this before, no? What is this? What is the unity gain frequency of this op-amp? GM1 by CL, that's all. So if you plot the Bode plot, what will it look like? So if you call this the transfer function to be A of S, if you plot A of S with S equals j omega as a function of omega, what does it look like? What will it be at very low frequencies? So it will be the DC gain, okay? A naught. And when does it start changing? So basically, you have one pole, right? What is the pole value? GDS1 plus GDS3 by CL, okay? So up to that frequency, roughly speaking, we can say all of the current flows here, and after that it flows over there. Of course, the transition is smooth, and then it does that. And as long as A naught is large, this you can write as GM1 by CL. In fact, let me write out the expression for A naught. A naught is GM1 by GDS1 plus GDS3. Okay. So basically, this has come down by, this is unity, right? This is 0 dB line or unity line. So this has come down by a factor A naught, and it's a first order dependence. So this moves out by a factor A naught. Okay. So these three are related. You can specify any two of them. It's common to specify the DC gain and the unity gain frequency. The pole, if you really want to, you can derive from that. But these are the crucial parameters of the op-amp, right? Is this okay? Now, is that it? Is this the transfer function of the op-amp, or is there something more to be considered? Okay. Where? But which is the one that would make a difference here? So there are other nodes also, right? I will consider only one of them. So you can have some parasitic capacitance there, and also you will have it here. Okay. Remember, this is not a symmetrical circuit. Okay. So this voltage is not incrementally at ground, even with fully differential inputs. Okay. If the circuit is symmetrical, then this will be at ground. So no current flows through that. In this case, the circuit is not symmetrical. So that also can have an effect. But I won't worry about that. I'll only look at this one. Okay. What is the effect of the CP? What does it do? What do you think? What will it do? It is? Okay. So what happens as a result? So, okay. Now, let's say we have VID by 2 and minus VID by 2. Okay. What is the output current when the frequency of VID is very small? Essentially DC, right? Very low frequencies. What will be the output current? Huh? GM1 times VID. Now, let's imagine we are operating at a very, very high frequency. Okay. What will be the output current? What will be the output current and why? Yeah, why? This if this CP becomes a short, okay, so all of the current from this simply goes into the short, it doesn't get mirrored. So at very high frequencies, again, it will be GM1 VID by 2. Okay. From this itself, you should be able to sort of write out. First, let's do this. The output current divided by VID. Okay. So this, first of all, what kind of transfer function is it? Will you be able to write it by inspection? What is the order of the transfer function? What is the order of the transfer function? This is, I am looking at the output current. Don't consider the output capacitor here. You can imagine that I have a voltage source which is terminating the output. I'm only looking at the output current. So what is the order of this transfer function? Huh? Yeah, you would consider CP, yes. First order. Okay. So if it is a first order thing, a lot of things can be done by inspection. So where is the pole? What is the pole frequency? How do you calculate the pole when you have only a first order circuit? You have one capacitor finally, and you have to look at the effective resistance across that capacitor. What is the effective resistance? Let's forget GDSs again. 1 by GM3. Okay, so that is this is diode connected. So it has a resistance 1 by GM3 or a conductance GM3. So what is the pole frequency? GM3 by CP. So the denominator will be S times CP by GM3. Okay. So now, what did we say? This at low frequencies, I out by VID. What did we say is that at low frequencies? I out by VID. What was it? GM1. At very high frequencies, GM1 by 2. Okay. If it has to be like this, what kind of transfer function do you need to have? One pole and one zero, right? Okay. That's the only way you're going to get like these two flat areas. No? So what is this frequency? We already know. It is GM3 by CP. So what is that frequency? Because you have come down by a factor of 2 this way, you have to go out by a factor of 2 that way. Okay. I think I had already mentioned this. If you have two paths to the output, that is, you have two different paths, they get added up. And if the two have different frequency responses, you tend to form zeros, right? You can think of like adding polynomials of S, right? So you have 1 by S plus A, something by S plus B, you wait and add these things, you can get S in the numerator also. Okay. So that's how it happens. So now this, again, these are the things you should try and do so that you first of all can do sanity checks and you can write down the answers quickly and so on. So this is the form of the transfer function, and what should be outside? What should be outside? GM1. Okay, because then at low frequencies you just have GM1. At very high frequencies you have GM1 by 2. Okay, so that's what it is. So if you look at the actual op-amp transfer function, what is that going to be? That is V out by VID. What will that be? Some of these things, I mean, if you throw all the small signal equivalents into the circuit, the result gets so messy that you won't be able to make out anything from that. Okay, so we have to do it approximately. Earlier we said it has just the DC gain and the first order roll off because of CL. Okay, now you have this other thing also. This is a pole zero pair. Okay, so in fact you can call this maybe GM1 of S or something, right? So the entire thing will be, the total response will be, there'll be, you need to know this. Okay, where P1 is GDS1 plus GDS3 by CL. And if I assume that this pole and zero are outside the unity gain frequency, you will end up getting something like that. Okay. So you will also have to get comfortable with estimating these things. That is, if you just want to put all the quantities in the circuit and calculate, you can do it probably with a symbolic calculator, but then you can't make sense. So you have to also know, that is the engineering that you learn, when to neglect GDS, when to include it, and so on, because that's what I've been doing, right? One step I have GDS, another one I don't, but it's not arbitrary. You have to be able to reason out when it is significant and when it's not. Okay. For instance, I mean, this GM3, obviously GM3 is the most dominant conductance here. It's diode connected. You can add GDS3 to it, but it doesn't really change much. Okay. Similarly, while calculating the common mode gain, from here to there, I took the gain to be 1. You can add this factor, but in the overall picture, that's not going to make much difference. Okay. So these are things that you have to get comfortable with. And this is true not only of circuits. You may or may not choose to do circuits in the future, but whatever it is that you do, you should know it at a level that, I mean, more than simply being able to calculate. Okay. Should get intuitive feel for whatever it is that you're doing. So what next? What else is there to calculate? Now, from now on, what we'll do is, we know that if we use this differential pair with current mirror, this is going to be the response, and we will use this. Okay. Is there any other? I think small signal wise we are done. We know DC, we know AC, and large signal wise, what are all the things to calculate? First are the swing limits. Again, you need to specify 2 swing limits. You have 2 inputs, but as usual, what we'll do is, we'll specify what are the swing limits you specify for an op-amp? What do you impose the limits on? Input common mode and the output voltage. Okay, because you never apply a voltage directly to the inputs of the op-amp, right? You use the op-amp in feedback, and the output is adjusted based on feedback. Okay, so you specify the limit on the output signal, and you specify the limit on the input common mode, so that you know how to bias it. Okay. So, and any common mode analysis with this structure can be done by shorting the drains of M1 and M2, because if you have only common mode input, then these 2 voltages will be the same in absence of mismatch. Okay. So what are the swing limits on VICM? This again, you should be able to recall results from earlier. What happens if you go on lowering VICM? Which transistor gets into trouble? Which one? M0, the current source. Because what will this voltage be? If the operating point current is 2I0, what will be that voltage? VICM minus VGS1 at a current I0. You can calculate all these things, but there is no point writing like square root of 2 mu blah 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 every time, right? You know how to calculate VGS, that's what it is. Now, this you have to leave enough room for M0 to be in the saturation region. So, the lowermost value of VICM that's possible is how much? So, this has to be greater than VD sat 0 at a current 2I 0. So, the minimum value of VICM is VGS1 at a current I0 plus VD sat 0 at a current 2I0 or VT plus VD sat 1 at a current I0 plus VD sat 0 at a current 2I0. Okay. If I go on increasing VICM, which transistor gets into trouble? Again, if you are not able to see this immediately, please go back and refresh your notes, refresh your memory from your earlier course. What is which transistor gets into trouble if you go on increasing VICM? M3. Why? So the current here, what happens to this current as you change VICM? Nothing. So these voltages don't change at all, right? So as you go on increasing this voltage is fixed. You go on increasing the gate voltage. For an NMOS, how much can you go? How far can you go? The drain voltage is fixed, the gate voltage is increasing. How far can you go? 1 VT above the drain. Okay. So what is this voltage to begin with? VDD minus VSG3 at a current of I0. And you can go 1 VT above that. So VTN, right? So this is basically VDD minus VTP minus VD sat 3 at a current I0. I'll use VD sat for both NMOS and PMOS plus VTN. Okay. So now if you look at the available room between 0 and VDD, okay, is the upper one closer to VDD or the lower one closer to 0? They are the same distance. Which side do you lose more? You can't go all the way to VDD, right? Similarly, you can't come all the way to ground. So which side are you losing more? Towards ground. Okay. First of all, you have two transistors, and then this one's VGS has to be accommodated. So on the lower side, you lose VT plus VD sat 1 plus VD sat 0. On the upper side, if you assume VTP and VTN are the same, you just lose VD sat 3. Okay. And this is the room available for the signal, considering only the common mode. Okay. So with an NMOS differential pair, you can go a lot closer to VDD than to ground. In fact, this may be one of the reasons to choose between NMOS and PMOS. If in your context, you need to go a lot closer to ground, what do you have to do? You have to use a PMOS differential pair with an NMOS current mirror load. Okay, in that case, everything is inverted, right? You can come closer to ground, but not towards VDD. And what is the output swing? On the output swing. Here I have to say something. So that is, I'll denote the total output by so much. Now, of course, output will change only if you apply some differential signal. Okay, but we assume that the differential signal is so small while calculating the swing limit. Remember, in case of the common source amplifier, you would have done this, right? The input changes by some Vi and this falls by some gain times Vi, and the two are coming close to each other. That's how you find the triode region limit and so on. But we'll assume that the gain is large enough. So the input voltage will always be small. We neglect that. Otherwise, again, the expressions become unwieldy. Okay. So it's not that we are doing something completely inconsistent from what we did earlier. It's just that that particular term is negligible. If A0 is very large, for a very small thing here, the movement of that is a lot more. So we consider only that. Okay. So what is the swing limit on the output? On the upper side, it is VDD minus VD sat 3 at a current of I0, and on the lower side, so if the gate is fixed, what can happen to the drain? How far can it go? It can come below the gate for an NMOS, but only by one threshold voltage. So it is VICM minus VTN. So this is also skewed towards the upper side. Okay. On top of it, the output swing is dependent on the input common mode voltage. Okay. Whatever input common mode voltage you have, you can go lower than that. We'll see the implications of this. We can do it for one particular case, and then after that, these things become automatic because we'll be reusing the same block, and you'll be able to evaluate them. Okay. This part I'm assuming you've already seen earlier, right? The swing limits of a differential pair. Okay, you should have seen that. If not, you go back to your notes and check it out. So the output limits would be, so again, you lose lot less on the upper side. You can go up to VDD minus VD sat 3, and on the lower side, it depends on VCM. It VICM. It is VICM minus VTN. Okay. Yeah, right. Yeah, it's basically the actual input common mode. So that's why, again, I won't go into the details now. So if you have something like this, right? What is the, in this, what the actual common mode voltage is depends on the circuit and what signals you apply, right? The swing limits, what do? They apply a constraint on, they give you a constraint on the signals that can be applied. Now in this case, it, it's slightly more complicated because you have two different swing limits. But what is the common mode voltage here? What is the common mode voltage in this circuit? This is Vi, right? I mean, this is a unity follower. We'll say assume V0 equal to Vi. So the input itself is the common mode voltage. If you have this, so if the input is a sinusoid, the common mode is also a sinusoid, and the output is the same sinusoid. Here, if the input is a sinusoid, the output is the opposite sinusoid. What is the common mode voltage? 0. The common mode doesn't change here. So this is where it comes in. So in this circuit, whatever signal you apply, right, it has to respect both the, in every circuit, both the common mode swing limit and the output swing limit have to be respected. In this case, the common mode is swinging. So the actual signal that you can apply could be limited by either the common mode swing limit or the output swing limit. You have to calculate and see. Whereas in this case, because the common mode is not moving, you can set the common mode to be in some range that is permissible, and after that you can let the signal be limited only by the output swing limit. Okay, that is one of the reasons why this is actually a lot more user friendly than the other one. It has its disadvantages, but it's what is more commonly used also. Okay, so this is how you use it. You have a swing limit on both the common mode and the output signals. So one way is you, assuming ideal op amps, you calculate the outputs, you calculate the common mode, and then you can put restrictions based on the common mode swing limit and the output swing limit. Of course, whichever is the worst case, that will be the limit. Okay. Okay then. See you all.